Sorry that I'm out today, but we have something that I don't think is too challenging, and we can teach you this in a video, and we can go over it on Monday, practice a little bit next week. We will have a quiz on this information on Tuesday. So the first thing is that we did a lab yesterday, and if you weren't here, we took 3 different metals. We took some aluminum, we took some brass, and we took some lead, and we took them and we boiled them in hot water, got them up to 100 degrees, and then we put them into cool water and we looked at how much the temperature changed. And what you will see is that the lead only changed the temperature a little bit, while the aluminum changed the temperature a whole lot. And we were talking about they're the same mass, they're all 30 grams. So how did this happen? And the last thing that we talked about before we went off for the day is we said they're because they have differences in specific heat capacity, and that each of these has a different ability to take in energy to heat itself up. So with that said, I hope that Mr. Kowaleski has passed out these papers. We are going to do some guided notes first, and then we're going to do a practice worksheet. So if you don't have these guided notes in your hands yet, pause the program and let's get these guided notes in your hand. All right, so I don't love guided notes, but I think it's so much easier if I'm not here to go ahead and go through this with you. So let's define specific heat capacity, and we'll try to tie this into the lab that we did yesterday. So first off, we have specific heat capacity is the definition of specific heat capacity is the amount of energy needed to increase the temperature of 1 gram of a substance by 1 degree Celsius. Okay. So it's the amount of energy needed to increase the temperature of 1 gram of a substance by 1 degree Celsius. So let's think how this ties into yesterday. This was 30 grams, the aluminum, and this was 30 grams, the lead. Obviously, it took a whole lot more energy to heat up these 30 grams in the aluminum than it did to heat up the 30 grams of the brass, because when they were transferred into the water, this one made it go up around 7 degrees, and this one only made it go up about a degree a little bit more. So while they were both at 100, this one took a whole lot more energy to get to 100 than this one took energy. Okay, to get to 100. So, or another way to think about it is how hard or easy it is to heat or cool something. So I like to kind of compare these bad boys to kind of like cleaning materials. So I have a paper towel, I have a little bit of a terry cloth towel, and then I have a sponge. And so while all these are kind of roughly the same shape and same size, kind of, not really, but they're all the same kind of idea, like our 3 metals were yesterday. So what I can say is that this little piece of lead, when it went into the boiling hot water, it didn't take a lot of energy to heat it up. So it's kind of like this paper towel. As soon as I put that in there, it's instantly wet. And how much can it transfer? It can't transfer very much because it didn't take very much to saturate it. Now, if I have something like my brass, which was the middle one here, and I can put these numbers back up here. Okay, this took a little bit more energy. So when that brass went in, it took a little bit more. Okay, it absorbed a little bit more energy on its way to getting to 100. So this has more to transfer, okay, as far as its energy goes. And then last but not least, we had the aluminum, which is going to have a very high specific heat capacity. It was 6.43 degrees Celsius change. So that means it went in to get 100 degrees, and it took a lot of energy and a lot of energy and a lot of energy and a lot of energy to even get that aluminum here up to 100 degrees. And so because it took a lot of energy to get the aluminum up to 100 degrees, it also has more energy to, okay, bit of a mess, more energy to transfer. Perfect. So that is what specific heat capacity is. Okay, so I just had to clean up that little bit of water, but now we're back. So we are talking about specific heat capacity, and it's the amount of energy needed to heat or cool 1 gram by 1 degree. So it's a cost. The easiest way sometimes to think about it is the unit. So the unit is joules per gram degree Celsius. So jot that down, joules per gram degree Celsius. And so sometimes if you don't remember the definition, if you remember the unit, it tells you it's how much energy, remember joules are energy, it takes to heat 1 gram or cool by 1 degree Celsius. So the unit often tells you what it is. Okay. So again, if you want to look at it a different way, it's how much energy it takes to heat 1 gram, 1 degree Celsius. So it's the cost. It is how much did it cost to heat up my aluminum? It cost a lot. So you can think about it as a cost to heat and cool, and every substance has its own, like its own density. Every substance has its own specific heat capacity as well. So every substance has its own cost to heat or cool. Some things heat and cool quickly, and some things do not heat and cool quickly. So the one thing we're going to talk a lot about is if you wanted to go home and you wanted to make some, not in the microwave mac and cheese, like a real box of macaroni and cheese, what is standing between you and having your delicious mac and cheese? What do you have to wait for? You always got to wait for the water to boil. And why you like put that on the stove and you watch it 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 and you watch it. And the reason why is you could have that on high, but it takes so much energy to heat that water up to get it to a boil. So that is a big cost or a high specific heat capacity. And so you are going to actually have to memorize that number. So we're kind of leading down here into the specific heat capacity of water. So the specific heat capacity of water is 4.18 joules per gram degree Celsius. That is a huge number. That is a lot of joules to pay to heat every 1 gram, 1 degree. So if you think about your big pot of water, it needs 4 plus joules to get every 1 gram to go 1 degree. And then it's got to go all the way up to 100, and you probably have lots and lots of grams. So you just got to be very careful with your specific heat capacities. If they're high, takes a lot of energy to heat it up. If they're low, it doesn't. So what you can probably see now is that our highest specific heat capacity would have been aluminum yesterday. And I'll give you the numbers here in a second. And the lowest specific heat capacity would have been lead. So it's again the amount of energy it takes to heat 1 gram of water, 1 degree Celsius is 4.18 joules. So 2 real world examples of that big number is, let's say it was a nice cold winter, and in March, let's say we hit a day that's 75 degrees Fahrenheit. Would you run and go jump into a pool, an in-ground pool? Absolutely not. Just because the air has heated up, that doesn't mean that the water in the ground has heated up at all. If you take a look on this little side on your page here, you can see I gave you some relative specific heat capacities. Dry air is very easy to heat and cool. Okay. However, water takes a ton of energy to heat up compared to that. So you wouldn't be able to run and jump in the pool because it's still cold in March. Just because it got warm outside doesn't mean that water is at all warm, because the sun can warm the air, but not the water. This is often really shown in like summer days as well. So let's say it gets cool in the evening, but it's been hot all day. You go outside, you stand on the cement. The cement might still be fairly warm because of all the energy that it gained, and then it's holding on to it and it's taking a while to release. So another thing, like when we were talking about radiations, probably talking about the sun, and convection currents are probably talking about weather or ocean currents. Water having such a high specific heat capacity is often why coastal towns have really nice weather. And I wrote a lot here. You don't have to write all this if you don't want. But so the coastal towns having that large body of water next to it, it takes a lot to heat and cool that water. And that keeps those coastal towns in a very temperate climate. So large amounts of water need a lot of energy to heat and cool. So if you have land next to that, that usually keeps it more at a relative temperature to the rest of the country. Perfect. All right. So if you didn't get all that, maybe we can pause that. I just have no idea of wait time when I'm leaving notes like this. All right. So we're on the back. So let's get into quantifying. So everybody wants to fire up a calculator here. Go ahead and make sure you got that going. But we have to learn how to put some numbers to this stuff. And so this is called the heat equation. And the heat equation looks like this. Q is equal to MC delta T. Q is equal to MC delta T. When you're super cool, you can call it Q is equal to MCAT. And that's probably because it's Friday the 13th and it looks like a black cat when you write. Absolutely looks like a cat. Oh, he needs more whiskers. No, okay, that was a horrible joke. I probably would have landed if I was there because I'm hilarious. But so it looks like Q is equal to MC with an AT. So people call this MCAT. And so let's break down these definitions here. What is Q? What is M? What is C? What is delta T? You probably can identify two of these very quickly. One you know for sure, and then the other one we talked about in the second set of notes for this unit. All right, so Q is quantity of thermal energy, or the amount of energy that can be transferred, so heat. So Q is quantity of thermal energy. And remember, we talked about the iceberg and the hot water, okay? Mass does matter when you're talking about thermal energy. So huge things with lots of particles has lots of Q because of all of that M. Okay. And the unit we said earlier for that, but just to reiterate, the unit for Q is joules, which is written as a J. M, you guys all know what that stands for. That's mass, and that's going to be written in grams. C is our new idea here. This is specific heat capacity. So each material will have its own specific heat capacity or its C value, and that is joules per gram degree Celsius. And you will have to memorize the water one, 4.18. I know your new favorite number is 4.18 now. It used to be 1.00 for the density of water, but now your new favorite number is 4.18 joules per gram degree Celsius. And then delta T. Okay, we know that T is temperature, and remember we said delta means change in temperature. And so I have a little plus sign here that I guess is confusing to everybody. It is always a positive number, but how do you get change in temperature? You subtract. So if you start at 10 degrees and you end at 12 degrees, remember from the lab yesterday, we subtracted those, and it is going to be in degrees Celsius. But whenever you put a number, a delta T, into MCAT, don't put in any negatives, just put in the positive. All right, so here's an example. I'll do a couple with you, and then we'll pass out the practice worksheet, and you guys will be able to do this. So an oven transfers 66,195 joules, I think I malfunctioned there for a second, of energy to an aluminum baking sheet with a mass of 425 grams. How many degrees does the temperature of the baking sheet change? And aluminum's specific heat capacity is 0.89 joules per gram degree Celsius. So the first thing I like to go through is I like to see if we can identify all of the variables. So I put these over here as kind of like a training wheel if you want to use them. I don't know that you need to, but if I see joules, 66,195, I know that's a Q. It is aluminum, so I need a specific heat capacity for aluminum, so that is C. 425 grams is my mass, and I want to know how many degrees that changes, so that is my delta T. So as you can see, I have 4 variables, and so I'm doing Q is equal to MC delta T. So I'm going to put Q out here is 66,195. My mass is 425. My C value is 0.89, and I'm looking for my delta T. Awesome. Now, a little bit of algebra here. I know you guys can all do this. So if I wanted to get this by itself on the side with delta T, I combine those first. So I do in my calculator 425 times 0.89, and that's going to get me 378.25. I was trying to erase, not paying attention. 378.25, and then that's times my delta T. And then I bring this number down here. And so sometimes students can get a little bit lost and they're like, okay, well, what do I do now? So I know algebraically, if I told you 4 was equal to 2x, you could absolutely tell me, all right, well, you just divide both sides by 2 to get x by itself. So I'm just going to divide both sides by whatever is stuck to my variable. So I'm going to take 378.25 and I'm going to divide both sides by that. So then that will get rid of, that will go to itself. And then when I do 66,195 divided by 378.25, you will get a number. And that number is 175. Now, I don't know where my other typing went. I should write 0, 0, because let's talk real fast for a second. Let's talk about sig figs. If your calculator spit out a number with a ton of decimals after it, could you ever tell me that you know that all of those figures are significant? Absolutely not. So what did we say our new rule is? Our new rule is that we will round 2 significant places after the decimal. So the only thing that gets really confusing on sometimes is when the numbers are small. Remember, leading zeros are never significant. So these would be 2 significant places after the decimal. So if you calculate a C value and it's 0.076 joules per gram degree Celsius, you need 2 numbers after the decimal. And remember, leading zeros never count. Okay, so I got my 175.00. And then the biggest thing that people always forget is you got to have a unit. And so if I wanted or if I wanted temperature, that means it was degrees Celsius. Okay, awesome. So why don't you go ahead and try number 2 and number 3 while Mr. Kowaleski passes out worksheet number 1 on this. Be very careful for number 3. I'd like to go through that one with you because sometimes that can be a little bit of a doozy. You tried these 2, so I'll go through them nice and quickly, and I'll do one of the ones on the worksheet, and then you guys are good to go. So what is the specific heat capacity, so what is C, of a substance that absorbs 2,500 joules, that is Q, of heat energy when a 100-gram sample, that's M, is increased from temperature from 10 to 70 degrees. There are 2 temperatures there. What are we going to do? So remember, delta T is change in temperature. So I'm just going to do 70. This is awful. Minus 10, which is going to give me 60. So once I went ahead and put these in here, and hopefully you got this, you got 2,500 is equal to 100 times C times 60. I'm going to combine those together. And then, in order to get C by itself, I'm going to divide 2,500 by 6,000. And when I divide that by 6,000, I get a nice small number, which is 0.42. Got to have a unit. And the unit for C, if you look at the top of that paper, is joules per gram degree Celsius. Oh, apparently I'm just giving answers over here. Wonderful. Hopefully you got that right. The hard one on this is that people think that there's only 3 values, which there are, but you have one in your head. How much thermal energy is released? So that's a typo. How much thermal energy is released? So that is Q. To your body when a cup of hot tea containing 200 grams of water is cooled from your body temperature to 37 degrees Celsius. So got your Q. That's what we're looking for. Your M is 200 grams. And then people are like, oh my goodness, I don't have a C value. Well, I'm sure some of you remembered that the C value for water is 4.18 joules per gram degree Celsius. And then my delta T, when I do 65 minus 37, is going to be 28 degrees. All you have to do is multiply those together, and then you put a J on for your unit. All right, so you have your worksheet in front of you. Hopefully they get an answer key to you. The quiz on this will be on Tuesday, so we'll go over it again this on Monday. Make sure you're good. I got a +3, +2, +1 for you on Monday, but let's get you into this practice worksheet before the end of the period. All right, so Q is equal to MC delta T. All right, so Q is joules. M is grams. C is joules per gram degree Celsius. and delta T is degrees Celsius. So what you really have to do, and this is setting you up for a lab situation, if you are asked a question, okay, and this one, I'm going to jump down to the bottom. I'm trying to figure out how much energy the sand lost. So when you do a Q is equal to MC delta T problem, the only variables that go into that are trying to answer your question. So I need Q of sand, C of sand, M of sand, and delta T of sand. Don't put anything else in here. Okay, so let's read through the problem now. It says, a 30-gram sample of sand was boiled in water until it reached a temperature of 100 degrees. The sand was then dropped into a cup containing 60 grams of lukewarm water that was at a temperature of 21.3 degrees Celsius. The final temperature of the water was 27.1 degrees Celsius. Calculate the amount of heat energy the sand lost. This is exactly what we did with our metals yesterday. Okay, so I need to pick out an M. I have 60 grams, but that's of water, so that's not what I want to use. If I'm trying to find the Q of the sand, I need the M of the sand. I need to multiply it by the C of the sand, which I have up here is 0.740. And then the delta T of the sand. So just like the metals yesterday, we took them and we boiled them to 100 degrees, and then we dropped them down to the joint temperature of 27.1. That was the final temperature. So your delta T is 100 minus 97.1, and then that gets me 72.9. Then we're going to multiply those together, and you're looking at 1,618.38 joules. That's how much energy the sand gave to that water, okay, or how much the sand lost to the water. Law of conservation of energy. So would you expect a brass sample of the same size? So if we had brass being the same size, 30 grams of it, would you expect brass to transfer more or less energy to the water if you did the exact same thing? And then would you expect if I cut the sample in half? And I want you to think about how those two things affect the Q on that. If I had a lower C value, what would that do to the Q? If I had a lower M, what would that do to the Q? So I'm not going to give you the answers on that. You can read the answers on here. I want you to think about it and say, do you think it would transfer more or less energy if we cut it in half? Okay, or if we used a different material based on its C value. So, all right. So at the end of the day, I hope that you can finish up the rest of these problems on here, check them with the answer key, and we will see you on Monday. Thank you, guys.